Hello. Now we are going to talk about k nearest neighbors. So, in the k nearest neighbors, basically this is a different type of machine learning algorithms, right? And later on we'll discuss about the SVM, which is again a very different kind of the algorithms, right? Till now, what we have discussed as an decision tree algorithm, right? We have discussed as what is supervised machine learning, what is cross validation, all these things, right? Now we are going to see a very different kind of the kind of machine learning algorithm, which is KNN. Right now, this KNN follow very simple rules. So basically, it follow this thought, which was given by the Aristotle's, right? So the thought was if two things are similar, right? So though so so the thought of one will tend to trigger the thought of others. That means if two elements are similar, right? So the both element features will be similar to each others, right? Consider that we have as an examples, right? Consider that we have the two laptops, right? As an again, it's a very simple example, right? Now the all the features of the laptops will be similar in both the products, right? So that is what the thought is, right? And the k nearest neighbor based on the very similar kind of thoughts, right? But before we start, let's just import few stuffs. Here we are importing all the stuff that is needed for this class, right? And what we'll see in this lecture, so basically we'll see what is the similarity based algorithms. We'll broadly explain this how KNN uses a distance algorithms, right? We'll see the effect of the hyperparameter k, right, in the KNN, right? In the last time when we discussed about this decision tree algorithm, in the decision tree algorithm, the hyperparameter we had discussed as in max depth, right? But we had discussed that there are other hyperparameter as well, like the maximum sample split or like max leaf node or something like that. So we had a lot of hyperparameter, but we just use the max depth. Here, the KNN, we have the K as an hyperparameter. We'll see what is the curse of dimensionality, and then after that we'll discuss the general idea of SVM and the RBF kernel, and then the SVM also have the different hyperparameter like the gamma and the C. It has this two hyperparameter. And we'll discuss everything in this class. First, let's understand. So, what is this analogy-based models? So, analogy-based model says that suppose you are given some training example. We have these training examples with some labels. So all the training example have labels. Again, all these training examples is very famous pictures, right? All the characters are very famous TV characters or the movie characters you can see, right? And so suppose we have this training example with the labels and asked to label the test example, right? So here we have this lot of these pictures along with the labels, and then we have this test example. We want to label what this person is or what would be the label of this pictures, and to figure it out what we have to do is we have to compare the feature of this persons to all the persons, right? And whichever person will be similar, the the like whichever the persons will be similar, that person's label will be labeled as the test example. Like over here in this case, this person label, which is Jim person, right? This person label, like this person features, this person features are very common, right? So we label this text example as a Jim person, right? So that is how the analogy based algorithm work. So the intuitive way to classify the test example is by finding the most similar example, as I have said, right, from the training set, and then we label that test example to that training example labels, right? And again, we can use this analogy based algorithm in many situations. Like we can build like we can use this so like this algorithm used in very high tech facial recognition systems. So it can be used in the future. Like basically what do we do is like in the facial recognition systems, right? We just collect the feature vector of the human faces, right? And then a KNN will help you to identify which feature which phase is kind of very much similar to the all the feature space. You can also build the recommendation systems, right? So there are lot of practical examples we have for the KNNs, right? So how the KNN works? So the general idea of the KNN is, and so again, to consider that, to understand that, consider these examples, these toy examples we have. We have this, here we have this toy example where we have this blue circle and the red triangle. Consider that the blue circle consider as in class 0 and the red triangle consider as in class 1, and we have the three green star, which are the test point, right? Now we these three green stars are the test point, and now we want to predict what would be the class for all these test examples. Now to find the class, what we'll do is we'll find the similar examples, or to find a similar example, what we can do is we'll say that if two things are close together, that means they are similar. This is like this analogy will be used, right? That means we have to find that which example is nearest to this star, which example is nearest to this one, and which example is nearest to this one, right? For that we can use the like, so whenever I'm saying the example, that means we are saying the nearest neighbor. That means we want to find the nearest neighbor for these examples, for these stars, this test point. That will help you to figure it out the label for these green stars, right? Here what we can do is, so currently we cannot see, just give me just a moment. Okay, here what we can see is, here we have seen so this code will help you to kind of visualize the different nearest neighbors and the examples, like over here, the with the n neighbor as 1, right? Here we can see that this star is nearest to this example, this star is nearest to this example, and this star is nearest to this example, and we'll say n neighbor is 2. Now, so now the two nearest neighbor for this star is this one and this one. Two nearest neighbor for this star is this one and this one, and so on over here, right? So, and here we can see that the nearest neighbor has 4. So here we can see that, like, based on how many nearest neighbor we want, right? So we can reveal all the nearest neighbors to the green stars, right? So basically, let's say that we want to take the decision based on one nearest neighbors. So what we can do? So one nearest neighbor is, when we say the one nearest neighbor, so let's say that here we're saying that if, as we have already discussed, that nearest neighbors to the test data point will be very much similar to this example. So here the nearest neighbor to this green star is this blue one. So this means that this blue example and then this green star both are very close, and as a result both example features will be same, right? Here as well, the this example and this red triangle features are similar. That's the reason they are close together. And over here, this blue circle and then this green star, both features are very much similar. That's the reason they are close together. This is how we think, right? So here, because both example are similar, so here we can label this green star as a class 0, we can label this green star as a class 1, and then we can label this green star as a class 0. And let's say that if you take decision based on the n neighbor 2, so now we have a tie. So now it says that now we have this one example belonging to class 0 and one example belonging to class 1. So we can choose the random. Here both example belongs to class 1. Here both example belongs to class 0. Let's choose n number as 3. Now with the n number 3, now we can see that that the two example belong to class 1 and the one example belong to class 0. So here we'll take the majority vote. We'll say that because this both like the highly numbers example, like these two examples are more, or the red triangle examples are more, so we'll label these example, this green star, as an class 1. Here in this case we still have the class 1 label, here we still have the class 0 label, right? So we can take decision based on n neighbors, right? And how do we calculate it? Basically we need to calculate the distance. We'll talk about that. Now let's talk about the geometric view of the tabular data and the dimension. Now to understand the analogy based algorithm, it's useful to think of data point as a high dimensional data, right? So every data point, let's say the image has the very high dimensional data, right? Or you can consider that our data point is following a high dimensional data space, right? So our x represent the problem in terms of relevant feature d with one dimension for each features, right? And examples are point in d-dimensional space. So here we can see that, right? So now what we have to understand over here is, like, most of our data point are follow high dimensional space, right? And it has this d dimensions, right? Consider these examples over here. We have the city data set. We have separated x and the y. We have this here we are just plotting our data over here. We can see that now we can see this data, we can visualize this data because this data is having the two-dimensional data. The first dimension is longitude and the second dimension is latitude, right? Let's see our Spotify data set. Here our Spotify data set have the 13 dimension because it has a 13 number of features, right? So in the tabular data, the number of features is called the number of dimension for the data, right? And most of the time it is a high dimensional data only, right? Let's try to run this. So in machine learning, the dimensions are very huge. Basically, we deal with the huge dimensional data, right? So again, when you have this data with the dimension as 20, consider that you have the low dimensional data. So high dimensional data is like 10,000, like 100 of 10, like 100 of 1,000 data is considered as a high dimensional data, right? So in machine learning domain, right, we usually cannot visualize the dimensional data, right? So we generally deal with the very high dimensional data space. Now again, understand few terms like feature vector. What is feature vector? So feature vector is composed of feature value associated with an examples. Consider that these examples we have. Here we are taking the feature vector of city dataset of first example. We are taking the Spotify dataset of the first examples. Here you can see that for the city dataset, this is called a feature vector. And for the Spotify dataset, this is our feature vector, right? So here, so to understand, the feature vector is nothing but it's a feature value in a vector. That is what the feature vector is. Now let's see how do we calculate the similarity between the two examples. Now to calculate the similarity between two examples, right? Let's consider the two examples over here. We have taken the two examples from the city data sets. One is 6935, and here we are plotting these two examples on this graph. We can see that these two black dots are the two example we have separated, right? And now let's say that if we want to know how much similar these two data points are, so the first thing comes in mind that to calculate the similarity we have to calculate the distance between both data points. That means if there are more distance between both data points, that means that much, like, if the distance between both data points are high, so there will be very low similarity, right? If the distance between both data points are low, then we'll have the very high similarity data points, right? So how do we calculate the distance between these two data points now? Now to calculate the distance between these two data points, we can use the Euclidean distance, right? Here, this is the formulas we have for the Euclidean distance, which is the u minus v, the square of that differences, and then we'll kind of take the sum of all the positional vector value, and then we take the root of that, right? That is how we calculate the Euclidean distance between two vectors. Now let's try to calculate the Euclidean distance. Here we have taken these two cities. The first thing is we need to do the subtraction. We need to do the square after that. Okay. So after that we'll sum them up, right? And then we'll take the square root. So here let's check the differences between two cities here. Now we are taking the square of the sum of the differences, and here we are taking the square root of the sum of the differences, right? So the difference between these two vectors is this, the square of sum is this, and when you take the square root it is become this, like so. Now we have the value as a 9.03, right? So this two city data set we have, right? And the distance between these two example is 9.03 Euclidean distance, right? It seems like you do not have to write this program by your own. Like we have this Euclidean distance functions available in the scikit-learn. We just need to import it. Here we are importing from scikit-learn, right? And we can simply pass this to vector, or we can pass this data frame entirely, and this will give you the distance between these two vectors, right? So essentially you can choose one. So this diagonal value that we are getting, right? So here the actual value is 9.03, right? So now let's talk about finding the nearest neighbors, right? So now we know how do we calculate the Euclidean distance between two cities. Now how do we find their nearest neighbors? Now to find the nearest neighbors, we have to find the distance between these example. We have to find the distance. Let's say that if you want to find the nearest neighbor for these examples, how do we find? Basically, we have to figure it out which is the nearest example to this black dot. Basically, by visually we can see that this red triangle is the nearest neighbors, but often this visualization is not possible because if we have the high dimensional data. So how do we use it? Basically what we can do is we can simply calculate the distance between these example and all the example into the training data set, and then what we'll do, we'll kind of sort the distances based in ascending order, right? And then the first example, which is at the shortest distance, will have the minimum distance between these examples. That is the one way that we can do, right? And here we'll do the same thing. Here we are calculating the distance between of each city with every other cities, right? So here it's like the distance between these examples. So here we have this distance between the zeroth example to the zeroth example will be 0. So here we have replaced with the infinity, right? Now the distance between the first example to the zeroth, so again, like here we are taking the distance between the zero example to first example, again the zero example to second example, again the zero example to third example, zero example to fourth example, and every other examples we are calculating. Right here we have calculated the distance between the zeroth example to all the example. We have the total 208 example, and same as we'll do for the every examples over here, right? And now we can do the similar things, right? So here we can take the first 5 examples, right? And after that we can kind of do the argmin. So argmin will basically it will give you the minimum distance value, right? So here the argmin is giving me that distance between city 0 is 81, and we can check the feature vector of the 81 is this, and the feature vector of the city 0 is this. Again, by looking at the feature vector we can see that their their values are very much close, right? So their longitude and latitude looks very much similar. So we can, in this way we can find that the closest city to city 0 is city 81, right? Now the question comes, so why do we set the diagonal entry to infinity? Like over here, we have set this diagonal entry to infinity, right, in this code. And we have done this because let's say that if you find the minimum distance to the city 0 to the city to all other city, so the city 0 to the city 0 will be 0, city 1 to the city 1 will be 0, so it will often come as a 0, so the first result will come as 0, so the same city will come, and we want to avoid that. For that reason we have kind of fill all the value, all the zeros value with the infinity over here, right? Now let's try to find the distance between, now will, well, basically now we'll find the distance of a new test example or a query city to all other city. For that, what we can do is, here we have taken the query examples and we have passed the city x city data set to the query example. What this will do is, this will calculate the distance between all the examples in the city to this query point, right? And here we can see the first 10 example of that, but here we want to know which city is the closest one. So what we can do is, we can simply find the argmin, right? And this argmin will give you the index, and then we can extract that index. Here we can see that the distance between this point, this query point, to to the city data set is with the index 71, and their distance value is 0.79, right? So this is how the KNN algorithm work, right? So here what we have done is, here we have taken the 30 sample of the city data set, and again we have this one cities, right? We have concatenated this, right? And after that, so here we have basically we have calculated, or we have taken a small training data set just to show the example, just to see the examples over here. So we have created a very small training data set, right? And then we have separated x and the y part of the training data set, and here we also have the test points, right? Basically this is the same test point we have, right? So here we have taken the test point, and then we have plotted all the data over here. Now here we have this all the data, and this is black dot is our test point, this blue dot is the USA, and the red triangle is the Canada. Sorry, yeah, so this blue circle is the Canada and the red triangle is the USA, right? Now, the given a new data point, we want to predict the class of data point by finding the closest point into the training data, right? Now to find, so now by finding is the nearest neighbors, or by doing the majority vote, we want to find the nearest example, or what would be the label for this example. Again, label for this example will be the label of the closest sample. Now first we have to find the which is the closest sample. For that we can use the this nearest neighbor things, right? So suppose we want to predict the class of the black points. So the intuitive way to do is the predict the same label as the closest, which is k as 1, right? So here if we consider as an n number 1, or like if we'll choose with the closest one, so here we can see that the closest one to this test point is the USA. Now we can label this black test data point as an USA, right? But how about k we are considering as greater than 1 to get the more robust estimation, right? We are not taking decision based on just one example. How about now we'll take decision based on 3 example or 5 example or the 7 example, right? For that we need to find all the nearest 7 example or all the nearest 5 example and so on, right? And then after that we have to do the voting. That means which one is the major one, or which one is the higher number. Let's say that here, if let's say that like here we can see that here if we are considering this n number as 3, so the one example belong to the US and 2 example belong to the Canada. So the majority is the Canada, right? Because Canada repeating 2 times, USA repeating 1 time. Now we can take the majority vote, and based on the majority vote we can label this black data point, this test data point, as in Canada, right? This is how we can use the nearest neighbors, and this is how this nearest neighbor work. First Here we are, how do we import this? So we are importing this k nearest classifier from the neighbor modules. Here we'll try the 2k, k as in 1 and 3. And now we are building models. Here we are initializing this nearest neighbors and applying the fit method, and then we are doing the predict method on the test data point. Based on the one neighbor, our model is predicting USA, and based on the three neighbors, our model is predicting Canada. This is what we have seen. Right here, this is based on the one neighbors and this is based on the three neighbors, right? So now the question comes as, how do we choose the k value? So the k value is called as an n neighbor in this. So here this n neighbor is the hyperparameters, right? We have to choose uh, this n neighbor value, right? So basically we have to kind of check what is the result comes with the n neighbor as 1, what is the result comes with the n neighbor as 3, what is the result comes as an n neighbor as 5, 7, 9, and so on, right? So because this is an hyperparameter, so as a user we have to choose the value of n neighbors, right? Now let's examine the effect of hyperparameter on the city data set, right? So here So here we have taken, so here we have separated X and the Y. We have splitted our data into the training and testing. Now here building models with the n neighbor as 1 and then applying the cross validation. Again, remember that we have discussed about the cross validation, which we use. So basically we use this cross validation to kind of take decision based on the validation data set, right? Here we can see that the training score always giving you 100% accuracy, but the test score here we are getting is very low. So here in this situation, it's clear sign of overfitting. That means our training score is high, but our test score is low. So this is a sign of overfitting. Now let's choose the k as 100. When we build the models based on the 100, and then after that when we choose this cross validation value, here we can see that with the n neighbor as 100, right? Our test score and the train score both are very low. So this is the situation of underfitting, right? So here now we have seen this both extreme examples. So we have seen the extreme example for the overfitting and the underfitting both, right? So we have to choose the anywhere value between 1 and 100, right? Here we are trying this different 3k value. Here we're trying the 3k value is k is on 1, 11, and 100. Here we can see that with the n number 1, our decision boundary is very much spiky. With n number 11, our decision boundary is much smoother. And with the n number, so here with this is with the n number 11 and this is with the n number 100. Here we can see that our decision boundary is not trying to be understanding the data. And we can also check the score of the data. Right here we can see that the score on the test train score is 82% and the score on the validation score is 80%, right? So by looking at all three example here we can see that our n neighbor so model which is trained on n neighbor 11 is the best model because in this situations, because in this scenario our train score and the validation score both are high, right? Now the question comes, how do we choose n neighbors? Again, n neighbor is hyperparameter, so we have to choose randomly, right? We can try a different value of hyperparameter and then based on that we can choose it. Here what we are doing is we have taken the n neighbor value between 1 and 50 with the 5-step value, and then we are training the multiple model with a different hyperparameter, and then we are again applying the cross validation. We are trying to check what is the training score, what is the validation score, and then here we are storing all the result. So we are kind of storing the n neighbor, we are storing this mean of train score, mean of cross validation score, and all the data we have, right? We are also storing this standard deviation for both cross validation and train score, right? Now let's see the result. Here when we see the result, we can see that, so this is our train mean train score and this is our mean CV score. Basically we'll take decision based on this mean of train score and the cross validation score only, and all this score is with the different n neighbors. So again the same formula that we have discussed in the last time, will take decision based on the cross validation. So we'll choose which model gives you the highest cross validation score. Here we can see that this model. So we can see that the model with the n neighbor 11 gives me the highest cross validation score, right? So now we'll choose this model, or like with n neighbor 11, right? Here we can also see the the graph of all this mean train score and the mean CV score. Again, this red one is for the cross validation and this blue one is for the train score. Here we can see that how things are, right? We can clearly see, right, how the value changes with the n neighbor changes, right? So we can simply choose the best neighbor, which is 11. Now after that, what we'll do is we'll again retrain the model with the 11 hyperparameter, and then we'll fit the model, and then we'll check the score on the test data. So here we can see that after we train the model, the score on the test data is 90%, right? Again, earlier we were not getting 90%, we were getting 80%. So seems like, right, because maybe because of some random numbers or some random value, right, we have got this high accuracy, right? But this is how we can choose the n neighbor value, right? Now there are other useful argument we have with the k neighbor classifier, like the weight parameter. That means when predicting labels, we can assign higher weight to the example which is closer to the query point, right? So we can kind of check that if this query point is closer to kind of like we can set the higher weight for that, right? And like we can choose a different weight parameter, right? Again, we can you can check the documentation of the k neighbor classifier in the scikit-learns. Now let's see how this KNN can be used for the regression task, right? So the question comes is, now we have solved the problems of classification with the k-neighbor algorithms. So can we again solve the regression task with the k-neighbor problems? So in the classification, we have used the voting technique. That means higher the vote, or like majority examples will have the higher vote, and the labels for the test data point will be the labels for the majority voted. But in the regression cases, we do not have that majority. So what we'll do, we'll take the average of the all the nearest neighbors, right? And sometimes we also call this as an weighted regressions, right? Again, here we can see that, consider that this example. So these are the test data point we have. These are the test data point we have with just one feature. Here we can see that we have the data point with just one features, and these are the target value, right? So here these are the training data set we have. Now this is the test data we have. Let's say that if we want to predict, like what would be the, like uh, if we want to predict what would be the value for the test example. So because it is one dimensional, but again, if you kind of plot in the, like plot in the, like take the straight line to the y-axis, right, we'll see that the closest example which comes to this star is this example, same as over here and same as over here. Here we are considering with the n number 1, consider with n number 3. So with n number 3, now the value have changed, right? So this star is closest to this example, and this examples, right? And now what we can do, and to get the exact target value for these example, what we can do is we can take the average of their target value, right? Here as well we'll take the average, and here as well we'll take the average of the target value, and that is how we'll use the k neighbor for the regression task. Now let's understand what are the pros of the KNN for supervised learning. Again, it's easy to understand, right? It's an interpretable models. It has very simple hyperparameter like the n neighbors, right? And we can learn very complex functions given the enough data. But it is a lazy learner. That means when we apply the fit method, it does not learn anything, right? What are the cons of the KNN? So it is very slow during the prediction time, because during the training time, it does not learn anything. it does all the calculation during the prediction time. So let's say that if we have the huge amount of data during the prediction time, it can take a large, like it can take huge amount, right? Now it is not that great model compared to the modern approaches, right? And it does not work well on the test with the many features. Like if you have the large amount of features, right? Consider that if you have the sparse data set, it does not work well, right? Now, now let's talk about what is parametric and the non-parametric model. So there are very lot of definitions we have with the parametric and the non-parametric model. But here, parametric model is something which gets trained during the training time. And the non-parametric model is something which gets trained during the prediction time, or which calculate everything during the prediction time. That is the non-parametric model. Like over here, KNN is our non-parametric model because it does not learn anything. It does not learn any parameter during the training time or during the fit time, right? Whereas decision tree is the parametric model because during the training time, it learns all the parameter. It learns which nodes to be splitted on. It learns what is the threshold value. All these are called the parameters, right? So there are two type of algorithms as well. We have this parameter and the non-parametric algorithms. Now let's see what is curse of dimensionality. Now this curse of dimensionality in general, what we see is like most of the model does not work well with the lot of features. Like the KNN, KNN is the algorithm which does not do great if we have the very high dimensional data, right? To understand that, consider this. Here we are creating this like here we are like this code. Basically, we are creating the feature from 4 to kind of 100 to 200 to 300 to 400 and so on, right? And every time we are trying to build a dummy classifier and the KNN classifier. Now we'll see, again, we already know the dummy classifier work. Basically, dummy classifier is just the random guesses, right? So it will give you approximately 50% of the accuracy. But the KNN classifier is the full-fledged machine learning model. It's not the random guess. And then we want to see how things change if the number of feature gets changed, right? And here we have stored all the result into this n feature accuracy matrix, right? And and here we are just trying to see the result. We can see that with the n feature 4, the dummy classifier value was 50% and the KNN was giving 94%. And here you can see that with the feature number is at this 1900, the dummy classifier accuracy is 51% and the KNN accuracy is 60%, which is very much similar to the dummy classifier, right? So what is the moral of the story is, so as the number of feature increased, our KNN model has started decreasing the accuracy. Here we can see that 94, 79, 70, 70, 60, 59, 66, again 58, we can see that. So here we can see that after the feature has growth to kind of 200 and like more than 200, our KNN algorithms accuracy has started decreasing. It works great if we have the less number of feature. Like here, when the n feature was 4, our model was performing 94% accurate, right? So this is the curse of dimensionality. That means our if the model gets like this KNN has this curse of dimensionality effect where so which means our model performance gets low as the number of feature gets increased, right? Now let's talk about the different algorithms which is called support vector machines. Hello, now we'll talk about support vector machines. Now again, we'll not discuss support vector machine at very good details, right? We'll see with the high levels how the support machine learning works, right? And how we can use the support vector machine with the scikit-learn. So the goal is we'll use scikit-learn SVM models. We'll explain the what is the support vector in the support vector machines. We'll see the similarity and the difference between KNN and the SVMs, and then we'll also see how this C and the gamma hyperparameter works. Right? And then we'll discuss basics of RBF kernels. Right. So this SVM is the another popular algorithms which is based on the similarity, right? And SVM is more likely work as an weighted KNN. That means the result of the weighted KNN and the result of the SVM both looks very much similar. The decision boundary is defined by the set of positive and the negative example, right? And their weights together with the similarity measures. And if a test example is labeled positive, if on average looks like a positive example, then the negative example. That means again we'll see like how this test example being classified with the graph. But the primary difference with the KNN and the SVM is basically SVM has the RBF kernels, right, which only remember the key examples, which is called the support vector. Whereas in the KNN we do not, we have to consider all the examples, right, to kind of classify any data points. SVM use a very different similarity matrix called kernels, right? And the popular kernel it uses as an RBF. So that's the reason we call this as an SVM RBF kernels, right? And they perform better than the KNs. Let's explore SVM over here. Here we have just plotted the examples. Again, we have plotted this Canada university data sets with the latitude and the longitude of the on the Y and the X axis. Here we have splitted our data into the training and into train and test. We have just first we are trying our k neighbor classifier with the best n neighbors, and with the cross validation we just want to check the scores. Here we can see that the mean of the validation score is 80%, and we can also see the, so like this is the like the total test score and the train score we have, and their mean score is 80%. Now let's see how the result comes with the SVAC. So now again the general name is SVM, which is support vector machine, but if you want to do the classification, they have the defined class called SVC, which is called the support vector classifier. So if you want to do the classification, you need to import SVC. If you want to do the regression, you need to import the SVR, right? Here we are getting the object of the SVC. We are passing to the cross validation to the entire training set. And then here we are trying to check the mean validation score. Here the mean validation score is 82%. Now we have this 2% improvement than the KNN, right? And that's the reason we say that SVM works better than the KNN. Now let's check the decision boundary of the SVM. Again, we can think of SVM with the RBF kernel as a smooth KNN. Like over here, we can see that this is the plot we have, this is the KNN plot we have, and this is the SVM plot we have. Here we can see that the KNN plot is very much irregular that we are seeing, but again, now the SVC plot is very much smooth compared to the KNN. And that's the reason we say that, right? It is more like a weighted or the smooth KNN, right? And that's the reason here we can see that, right? So their result of the SVM and the KNN both are very much similar, but both works very differently, right? Now let's understand what is support vector in the support vector machine, right? So each training example can become support vector or cannot become the support vector. So basically the support vector in the support vector machine is nothing but a training example only, but not all the training example we like consider as a support vector. So how many training example can be considered as a support vector? We do not know. That gets decided during the fit time. That means when we train the model, it gets decided, right? And the main insights is the decision boundary only depend on the support vector, right? So that means here these decision boundary is depend on the support vector only, right? And what is support vector? It is nothing but the examples only which is close to their decision boundary, right? Let's see. Here we are creating a simple data set with by using make blob functions. So here we are just creating a toy data set with the two class classifications. and here we are plotting it. So this is the data we have plotted, right, and divided based on the SVM, right? Now with the two features we have, so this is the boundary that we have got from the SVM. Now let's see which is the support vector. So again, to get the support vector, we can simply call dot support, and here we'll see these values. So basically this is the index of the value. So the third index value, eighth index value, ninth index value, 14th index value, all these examples. So here we are getting the index of the examples. All these example is considered as a support vector in the SVM, right? And this gets decided when we build the models. And again, these examples is nothing but the nearest point than the decision boundary. Like this is the decision boundary we have. This is the nearest point. This is the nearest point. All these are the nearest points, right? So only the nearest points will be the support vector. And here we can see over here in this graph, right? So these two are the so this larger examples, we can see that these two are the support vector, and here all these are the support vector we have. So basically only the support vector will decide how the decision boundary will be, right? And thus based on the support vector only, we'll see that if the example belonging to the specific part of the data, let's say that we have the new example and if you want to classify it, right, so it will first check whether like at which decision boundary, at which side of the decision boundary we are getting it, or that example falls in, and then that example will be considered as an that like that example will be labeled as that class, right? So if the new example falls in this region, so it will consider as a class, like let's say that the like red triangle, or if the example falls in this category, so or like falls in this side, it will be labeled as blue circles, right? Now we also have the hyperparameter of the SVM. So we have the two hyperparameter like the gamma and the C, right? And again, will not understand how the RBF, like here will not discuss how the RBF kernel works, but consider that it is one of the main functionality of the SVM model. It's a main pillar of the SVM model. Without it, SVM model is like SVM algorithm is nothing, right? Still, we have the different kernels, right? But again, if you want to know the kernels, right, you can click on this link and read the documentation. But you just understand in this way that kernel is something which plot the data into the higher dimensional space, right? Not plot, that means which takes out the data into the higher dimensional space. So by keeping the data into the higher dimension space, or by pushing the data into the higher dimension space, right, we this algorithm try to kind of try to define the boundary for the for the decision for the SVM algorithms, right? So here how the gamma works. So gamma control the complexity just like the hyperparameter we have. Like the large gamma means more complex model and small gamma means less complex model. Here we can check with a different gamma value. Here we have this gamma value of 0.001. We can see that we have this very kind of shallow models, right, where the training score is 78%. With the gamma model is 0.01. We have the training score as 84%. We have the gamma model of 0.0 like 0.1. The training score is 86%. As we can see, as the gamma model increases, the training score increases, right? And how the C works. So C also works the very similar way. The large C means more complex and small C means less complex. Let's check the different value of C. Here with the C value of 0.1, we can see that we have the underfitted model with the C value of 1. We have this good model like 84.84. We have this 187, 1088, and then we have this 100,000 is 90. So here we can see that how the gamma and C work. Basically, we have to choose this both gamma and the C over here, and the best value basically we decide based on the validation data, not on the training data. But again, I hope essentially you get how the gamma and the C works, right? So now we have to do again. to kind of find the best hyperparameter, we can choose the, or we can use the cross validation techniques, right? And based on the validation accuracy or the error will decide which good value of gamma and the C value are. But again, consider that we have here we only have the two hyperparameter, but let's say that there would be the model where we'll have this 3 and the 5 and the 10 hyperparameter. In that case, our problems will become complicated, right? Now, in that scenario, we'll use these two algorithms like grid search CV and the randomized search CV. These two algorithms will help you to decide which, like kind of, it will help you to decide which hyperparameter is the best hyperparameter, right? Or it will help you to decide the best hyperparameter for this particular models, right? Now, if you want to use SVM for the regression algorithm, again, it's a very similar algorithm. We just need to import SVR, right? And again, if you want to know this SVR into the more detail, just check the documentation in the scikit-learn, right? That will help you a lot, right? And here, this is our interactive playground with the SVM and the support vector and the decision tree. Here we can see that we have this iris data set. We have this function to plot the result. We have the different parameter like C, gamma, and neighbors, max depth. We have this function to plot the data with the different models, right? So this is the interactive dashboard we have, right? If you want to play with it, right, you just need to kind of run the code, right? And it will help you, and like it will display the interactive dashboard, right? And then you can kind of test it at the different hyperparameter and which algorithm works great with the different hyperparameter, right? And again, this will be based on the iris data set, right? So you need to run it and then try it once you get the the file with you, right? And yeah, that's it, right? So what we have discussed, in summary, we have discussed how the KNN and the SVM work. We have discussed this analogy-based algorithm. We have discussed how the decision tree is different than the SVM and the KNN. We have discussed how the KNN have the curse of dimensionality, right? And again, we have also discussed that we can use this decision tree. We can use this KNN. We can use SVM. All this algorithm we can use for both classification and regression both, right? And then later on we'll kind of discuss more real world we'll kind of see machine learning on more real world data set, right? But for now, thank you very much.